So welcome to the last session of ADAS 2020. We have a few talks, and then we have the prize talk, and then we have some closing remarks. Our first talk is about machine learning for the Zwicky Transient Facility by Dmitry Duev, who is from Caltech and is giving the invited talk on this session. Take it away, Dmitry.
Thank you so much. Let me start by saying a few words of appreciation for the organizers of this conference. I've been really enjoying it. I'm really thankful for the invitation and for the for this possibility to talk to you. So I, as said, I'm a research scientist at the astronomy department at Caltech, and I'm going to talk about the machine learning applications for the Zwicky Transient Facility. If for some reason you are not familiar with the Zwicky Transient Facility, so it's I would say an industrial scale robotic optical sky survey that is using the 48-inch Schmidt telescope at Palomar Mountain in Southern California. It performs accurate measurements of billions of astronomical objects and registers an order of 1 million of transient events every night. So I'm not sure if you can see my mouse, but this is the Palomar Mountain. On the bottom right is the P48-inch telescope. That's how large the camera is. That's where it sits inside the 48-inch telescope tube with the robotic end that does the filter exchange, and this is the first light image of Andromeda. ZTF at a glance, very large camera. The active detect area 47 square degrees can in principle survey the entire northern sky that is visible from Palomar. Nominal exposure time, in a nominal exposure time of 30 seconds, we get down to something like 20.5 at in the R, the image quality of 2 arcsecond. Main science drivers for ZTF have been the following, as many of you know. So it's we're interested in fast, young, and rare flux transients, looking for counterparts to gravitational wave sources, low Z type 1a supernovae for cosmology, all sorts of variable star signs, eclipsing binaries, solar system objects. If you want to learn more, please go to our website. On this slide, it's kind of messy. I'm showing the data processing flow as of the end of the ZTF phase 1, which completed just a month ago, and we've entered phase 2 on October 1st for another 3 years of operation. The key point here is that there are all sorts of pipelines that produce all sorts of data products, such as the famous transient alerts, but then also streaks detected from fast-moving objects, photometric time series / light curves, and all those are consumed by a wide range of processes and services. Whichever way you look at this diagram, it is teeming with vast amounts of data and highly nonlinear mappings. And we all know that this is exactly where machine and deep learning excel. So what are we using machine and deep learning for? I will unfortunately not have the time to go over all applications, but I will put some of them in the spotlight in this talk. Among those are alert classification, identification of streaking near-Earth asteroids, then identification and localization of comets, classification of variable objects, classification of spectra taken with the SEDM machine, so the main workhorse that we've been using for classifying discoveries, supernova-like discoveries made with ZTF. Then predicting behavior of AGN, fixing the focus model for the telescope itself, looking for all sorts of anomalies and all sorts of our data, deconvolving images in dense field, and the list goes on. Let me start with the famous transient alerts. So these little packets that we send out every night, and hundreds of thousands or like up to 1 million, that contain cutout images of the part of the sky where an event has happened, with a rolling 30-day window light curve or photometry history, plus a whole bunch of metadata, including some machine learning scores in there. We've been using a system called Braai, which stands for something like bogus real adversarial AI, which is a CNN ConvNet-based real bogus classifier that yields something like an order of 1% false negative rate and false positive rate, and gives yields consistent performance across the phase space. Shifting gears back to our solar system, for the so many of you may know that the number of streaks that ZTF detects is every night, rather streak candidates, is essentially the same as the number of alerts that we produce, or even larger. But the number of false positives there is just astonishing. It's a couple orders of magnitude more than that for the alerts, and it's a challenging task to identify actual fast-moving objects or near-Earth objects among those. And for that, we're using a system called DeepStreaks, which uses an ensemble of ConvNet-based classifiers and achieves false negative and false positive rates that are well below 1%, which actually gives something like a 100x improvement over previous generation system that was deployed before we rolled this one out. To date, we've discovered over 180 near-Earth asteroids, some of them pretty interesting. And also should mention that the similar number was lost due to insufficient follow-up, because we tend to find fainter stuff that moves real fast, and it's real. If you don't follow it up in a timely manner, then that's it, it's gone. Till next time. Staying in the solar system, another system that I'm very excited about, we call TAILS, and we use it for deep learning assisted discovery of comets. It uses a state-of-the-art object detection neural architecture called efficient DET that we highly customized for this task. We've assembled a very large and diverse training data set as essentially in all other applications. And with the help of deep learning, active learning, sorry, have been able to achieve over 99% label prediction accuracy. So it looks at the images and tells you whether there's a comet and then in it, and then it also tells you where exactly it's located, and that is done with a precision of one to 2 pixel median positional root mean square error with respect to the nucleus position of comets as reported by JPL Horizons for known objects. We've been running it in production since late August this year, and it typically produces something like 10 to 20 nightly candidates. It works on stacks of images, either just science reference and difference image for a given patch of sky. But then we've actually found out that it works as well if you ditch the difference image, so no difference image required for the same kind of performance. And very exciting, we got our first AI-assisted comet discovery last month, C2020 T2, discovered on October 7 in the Twilight Survey data of ZTF. It's just a very nice demonstration of the fact that this stuff works really well, and we're looking forward for more discoveries. Shifting gears again, let me talk a little bit about the project we've spent quite a bit of time this year on. It's called SCOPE, which is some sort of an acronym for the ZTF Variable Source Classification Project. And we've started off with a pilot study. We selected 20 fields that are kind of representative of what ZTF is looking at, with 34 million objects in them. We've done a lot of work on the features, nomenclature, data assembly, data set labeling, and so on. And I'll go over all these points in the next slides. The key point here is that we are building in this project, one of the things we're doing is we're building labeled data sets and machine learning pipelines that are now being scaled and extended to the entire ZTF data. First publication is out, and the second one is currently under review, so I'm expecting it to be published very soon as well. Few words about the nomenclature and the classification scheme. We've spent quite a bit of time figuring out how to do that best, and what we converged on is a scheme where we separate the phenomenological and what we call ontological classes. And so in the first case, basically those classes tell you, in those classes, it's everything that can be said about a source given just the ZTF data. And in the second case, not just the ZTF data. And the classes and labels we organized in a tree-like structure, but each leaf of that tree we treat independently. So we get a set of independent binary classifiers. Essentially, every one of them tells you how likely is that this particular source is of class X. And it actually gives you quite a bit of power, in that if you know that the performance for one particular class is not great, you can tune and improve it without affecting the performance for other classes for which you're happy with the performance. We've selected a subset of the full class tree for this pilot project, and I'm showing it here on the bottom right. And another nice feature of that scheme is that you essentially get anomaly detection out of the box. So by playing around with these range sliders, sort of, we've been able to find lots and lots of very interesting objects. We've been using a set of features for classification. So all light curves with at least 50 epochs for now in those selected fields have been period searched using these three algorithms, for all of which we now have a very efficient GPU implementation. Plus, we've been using a system called Kowalski to feed in the data, and I'll talk a little bit about Kowalski at the end of my presentation. And that approach delivers scalability, and essentially now we've done the same for the full ZTF data set as it is of now. We've been using respectable, I would call it, variability features. See a paper from Kirill Sokolovsky from 2016. We've also been using graphical representations of the light curves themselves, condensed into this second order characteristic of them, the MDTs. And we've cross-matched all that data with 10 external catalogs, and that's the data that is fed into the classifiers. Labeling all that data is no small task, and we've built quite a few interfaces for data labeling and exploration, and I'm showing some of the examples here. So you need something that is fast and API driven, and also provides you interactive access to all sorts of information about sources in bulk. And this has resulted in one of the, I guess, largest data sets, labeled data sets for that kind of task, with over 200,000 individual labeled light curves so far, probably even more. Some sources do come from CRTS, like projects like CRTS and OGLE, and as one would expect, some classes are more numerous than others. We've been quantizing labels to 0, 0, 25, 0.5, 0.75, and 1 for label smoothing that we're planning to use in the future. And we've been we've been employing an, I would say, active learning like procedure, where we would start off with ZTF light curves and external data, cross-match them, produce external features, then pre-process the ZTF light curves themselves, and extract features from them, ingest all that into a fast database, and sample that to build a seed set that is then fed into human expert labeling, out of which comes a training / validation / data set, which we use for training classifiers. And we evaluate that. The classifications scores are put back into the database, and then essentially we do this loop where we would sample, would select, and inspect random or most confident and or close to decision boundary and or highest loss examples. We label them, we add them to training set, retrain and repeat again. And with that approach, we've been marching down the nomenclature tree. We've been using 2 families of classifiers, deep nets, kind of hybrid, using both dense networks or MLPs for the features part, and convnets for the DMDTs, and also XGBoost. In both cases, using hyperparameter tuning to find the best performing architectures. This is just a slide that I like to show on how the different classes group together in the training set. So that's a t-SNE representation of variable versus non-variable, and this is only variable stuff. And out of that, 10 classes were selected. Here I'm showing the kind of performance that we're getting. So I said essentially for every object you get a set of dozens of different scores, and you can play around with them. But then we've assembled test data sets on which we test the performance of all the classifiers, and we've been getting figures like that. So say, for example, for flaring stars, you see that they are variable, but they're not periodic, and they're flaring and not all other stuff. And then with these diagrams, you can immediately see in which cases our classifiers don't perform that well. And that in many cases just has to do with the fact that we don't have too many examples for some of the classes. So stay tuned for the full data set where we're going to switch to that once the pilot project is finalized and published. The results are published. Switching gears again, another project that I would like to highlight here is called SNlascore. And the intent here is to automatically classify spectra taken with the SED machine, so the main workhorse that sits on the P60 telescope, the same mountain. And essentially it looks at the spectrum taken with SEDM and tells you whether it's a SN1A or not, and also tells you what its redshift is, and it yields exceptional performance. And with some reasonable score cutout, you send the false negative rate drops below half a percent, and this will allow automatic classification and uploads to the TNS without any delay in ZTF phase 2. This work has been led by Christopher Fremling and Yashish Sharma. Coming back to the very beginning of my talk, this is what the data processing flow has been as of ZTF phase 1. And you can see the right side is kind of clunky. There's a whole bunch of stuff. And what I'd like to use the remainder of my time to feature a project that we've been working on since this February. So what we've done is essentially, well, we've decided to condense all these little pieces into a single system that we call Fritz. And the vision behind Fritz is to use it as the main science data platform for ZTF phase 2. And this is essentially an all you can eat, like everything in one box kind of product. It features a multi-survey data archive and alert broker. It features a marshal for all science cases that we have: the transient, the variable, the solar system. This Fritz would be the workhorse for the ML applications and active learning to deliver classification and labeling at scale, and could also be used, and it is also used as a follow-up observation manager, or TOM, as some would call it. Just wanted to highlight the wonderful people that I've been working with. These are the core. These people are the core dev team of Fritz. It's a joint Caltech/UC Berkeley initiative, but people from other places have contributed as well. This is essentially the schematic overview of how I understand Fritz. The task is to observe stuff, mine the data sets, discover interesting things, study and characterize them, and then publish them in Nature and other wonderful journals. Fritz, what it does, it combines together two major software pieces called Kowalski and SkyPortal. The first one is the takes care of the data archive and brokering stuff, and SkyPortal serves as the rest of the needs. I unfortunately don't have too much time to talk about Fritz in more detail, but I can do that. I mean, I can spend hours talking about it. So let me just name some of the features that it has to offer. So it's fully open source, as I should say, essentially everything that we've been producing. Once published and accepted, we open source the code and share the models that we build, and where possible, the data sets as well. It gives you powerful alert stream enhancement and filtering capabilities. It features extendable and scalable design. It's an API first system. All interactions are performed using APIs. Fine-grained access control. Yes.
You have 1 minute left.
Okay, thank you. So let me just leave you with this slide and show you some screenshots of how it looks in the wild at the moment. So thank you very much.
All right. Let's play the applause here. And then open the floor to questions. We have one question in the Q&A from Harold. Do you have unlabeled light curves? If so, what fraction is that?
I'm sorry, could you repeat that?
It says, do you have unlabeled light curves? If so, what fraction is that?
Oh yeah, that's the vast majority of them. So like well over 95%, I would say, are unlabeled. Even given that we labeled like 200,000 light curves by hand. But we do have a tag for each and every light curve at this point. It's just that we haven't looked at all of them with our eyes.
Right. My question is how specific is your how specific to ZTF is machine learning for your method of finding comets? Like I have a giant pile of megacam data, which is a different telescope and a different instrument and all that sort of thing. Can I sort of drop in a bunch of megacam data and find comets with it, or?
This is the hope. So even though it has been trained only on ZTF data, but I don't really see why it would not work for other telescopes. You do need to do some transfer learning for sure. And once released, we'll showcase how to do that with the data of other surveys. So that's really the hope, so that everyone can use that piece of software and look for comets. And we've seen that with other systems that we've put out, that other people took them, did a little bit of transfer learning, and got really good results.
And so
yeah, feel free to contact me. Like it could be a nice showcase.
Yeah. And same with the streak detector for the fast moving objects and so on. That also
the same. Yeah, the same.
Cool.
Trained on ZTF data only, but in principle can be applied to anything with a little bit of transfer learning.
I assume the LSST people are talking to the Vera Rubin people are talking to you extensively, since you. I mean, I had the same.
To some extent, yes.
So I mean, you've sort of done everything that they're planning to do. I mean, slightly smaller data set, but not a lot smaller, really. And it all seems to be working quite well. So there, to some extent, or
yes, I'm not directly involved with the LSST, but definitely we've been talking over the years, and this is also one of the bigger intents to help the community prepare for what's to come. So essentially, all of that can be taken off the shelf and applied to the LSST data, with again a little bit of transfer learning, but the hope is to make it as easy as possible.
all right. Oh, okay. Rob Seaman asks, the major NEO surveys do not rely on streak detection for most discoveries. Rather, moving object detection results from various tracklet techniques. To what extent does ZTF depend on correlating multiple detections, whether for moving objects or otherwise? That is, depend on correlations for discovery itself, not characterization.
So there are actually multiple pipelines that are involved in the discovery of near-Earth objects, and one of them is exactly what you're talking about. So it looks for point source-like detections, and it combines them into sets, tracklets, then does orbit fitting and all the traditional stuff. And streaks are specifically for things that are not picked up by that pipeline because they move too fast and they streak. So yeah, my answer would be there are all sorts of pipelines that do both things, and we're just trying to optimize for the particular use case. So whatever works best in a given case, we do.
Okay, I'm looking at the Discord and I'm looking at the Q&A, and I'm not seeing any further questions. So let's thank Dmitry for his excellent talk, and that takes us to exactly the bottom of the hour.
Thank you so much.